Welcome. It's about 10 years ago I was suggesting in a research problem to prove that any two manifold or two sphere in particular can be colored with 4 colors. I thought this is easy because I just discovered that level surfaces in a d-manifold are always d-1 manifolds or empty. So I was very excited and thought this is kind of, you can use these level curves to color things, you have more structure to color things. It turned out to be completely off because there is a result of Hassler-Whitney, who essentially proved that a maximally planar graph which is 3 connected has to be a 2-sphere. A 2-sphere is a 2-manifold which becomes contractible if you take a point away, but every unit sphere is a 1-dimensional sphere. It's a cyclic graph with 4 or more elements. And then you can look at the coloring problem, and in this case you can color it with 4 colors. It's a 4-color theorem, you can explicitly do it. In this case with a golf ball, the golf ball is nice because all the vertex degrees are 4 or 6, so this is Eulerian. If it's Eulerian, that Heawood has already found. If you have an Eulerian 2-dimensional sphere, then it's colorable with 3 colors. You just go around, you take a triangle, color it, and then you go and use the triangles to color it everywhere else, and you never really get into a trouble by turning around, right? If you turn around and you have 5 triangles, you get into a problem and you need more than 3 colors. But if every vertex degree is even, then you can do it with 3 colors. So that's Heawood's intuition, and it works also in higher dimensions. So for that you have to look at more generally at Fisk manifolds. So if you have a d-dimensional manifold, you can look at d-2-dimensional simplices, which here in this case are just vertices, and then you can look at the intersection of the unit spheres of all the vertices in this simplex, which is in this case just a unit sphere. And these unit spheres, the unit spheres here, have degree 5 or 6. You take the vertices which have odd degree. So in this case the Fisk manifold is just a 0-dimensional manifold with 12 points. In this case the Fisk manifold is empty because it's Eulerian. So in this case you just look at this dual sphere and you see whether it is even or odd. And that works in higher dimensions too. So in 3 dimensions, when you take an edge, in 3 dimensions, and you have all these tetrahedra hanging around, and if this is even for every of the edges, then you can color with 4 colors. No problem, because you just can color every tetrahedron. Just have this here. So what you can do is you can take a tetrahedron, you color it with 4 colors, and then you go around the edge and you color every tetrahedron. And if it's even, you can do that without getting into trouble, right? You can color everything, and then you go to the next edge and you can color everything. So that's this Heawood idea. So if the Fisk manifold, in this case just the edges for which this dual sphere is odd, is empty, then you can color with 4 colors. And that works in higher dimensions too. It doesn't work for tori, for example, or kind of not simply connected or projective planes. By the way, Jenny Nitishinskaya has immediately, she got a projective plane which needed 5 manifold, a 2-dimensional manifold which needed 5 colors. And the reason is it's not simply connected. So this Heawood argument needs simply connectivity. I got into this again in the context of relativity, right? In the Regge calculus, what you look at the triangle, and you have a 4-dimensional manifold, and then you look at the triangle, right? Triangles are then the d-2 simplices, 2-dimensional simplices, and then you take the intersection of 3 unit spheres. And this intersection is then, of course, just a 1-dimensional sphere. It's the unit sphere and unit sphere and unit sphere. And by recursion, you have every time you have a sphere. So this is a 1 sphere. It's a circular. And Regge has suggested just to look at the you know, kind of the excess angle, which essentially means the length in the discrete of this sphere, kind of as a version of curvature. But we can look at also whether it's even or odd. And if it's even always, it's kind of an Eulerian case, then you can color the D sphere with d+1 colors. No problem, it's the same idea than what he would did. You can color one of the maximal simplices with d+1 colors, and then you go around and you never get into a trouble, because when you go around, the only problem you can get if you go around a circular graph which is not not even, then you would get into trouble. So you don't get into trouble if this Fisk manifold is empty. We got then interested in topological graph coloring frameworks, and Stephen Fisk, who died relatively early with 63, he was a grad student here, originally a student of Giancarlo Rota, and he worked on two spheres here. His thesis was about triangularizations of two-dimensional spheres, and he was looking at more, you know, topological, you know, concepts in graph coloring. And one of the things you can do is you can look at the coloring problem as follows. If you want to color a two-dimensional sphere, which is the hardest thing, which you need to do when you want to prove the four-color theorem, what you do is you fill it up with a ball, as a ball, so you have a boundary of a three-dimensional ball. Then you look at the Fisk manifold in this ball, which is now kind of consists of knots and links and tangles. So it can also be at the boundary, can hit the boundary, so you have tangles. So it's kind of an interesting topological framework. And this Fisk manifold, one can show, is always a union of subsets. So it's a union of subsets, and each subset generates a manifold or manifold with boundary. It's not difficult to prove, because what you do is you can just verify that if you have for example, in this case here, if you have an edge is in the Fisk manifold, what happens is then you look at the unit sphere. On the unit sphere, this corresponds to an odd point with odd degree. There has to be always, by the Euler handshake formula, another vertex which has odd degree, and so you can continue it. And so because you can continue with pairs, you can write it as a union of one-dimensional parts. It's not unique, this decomposition, so you can do it in many different ways, but you can do it in one way. But it's still complicated. If you look at these Fisk manifolds, they are in general complicated. For example, I just looked at Fisk manifolds. In four manifolds, they're unions of two manifolds. For example, when you take a join of an icosahedron with a circular graph, what happens is the Fisk manifold just consists always of 12 octahedra, which are kind of, you know, altogether they can intersect, but they are a union of octahedra. So that's this result here. And then I got into this refinement, this barycentric refinement, and one of the things which really kind of made me excited, both in relativity setup as well as in graph coloring setup, that this length of this dual spheres does not change when you do a refinement. For barycentric refinement, yes, if you take a barycentric refinement, this Fisk manifold gets away completely. So this is automatically d+1 colorable for any manifold. You take any manifold, it doesn't even have to be a sphere. You take the barycentric refinement, because the dimension is now the dimension which you originally had as a simplex. These are the new vertices. You can take this dimension function as a coloring, so it's always d+1 colorable. But when you take the soft barycentric refinement, if you take the second highest dimensional simplices away, and you connect two highest dimensional simplices, two facets, if they are adjacent in this, and then you get the soft barycentric refinement, which is much nicer, behaves much nicer. For example, if I take the soft barycentric refinement of that, it again looks like that it's like a full array thing with 5 or 6 vertices. So the 5 degree doesn't change, and the 6 there are more vertices of course coming in, and all these vertices have degree 6. So that happens also in higher dimension. It's kind of nicely smooths out the manifold. The vertex degrees grow, but this length of the dual spheres does not change. So that's exciting because it's kind of like a curvature which doesn't change. So I like that, and it also doesn't change because it doesn't change the length. It doesn't change the Fisk manifold. It just refines the Fisk manifold. So this might actually help to do this constructive coloring, which you can do in graph theory, which is kind of the idea is kind of just you get rid of all these Fisk manifold by edge refinement. So that's a procedure. I think it works, but one has really to, in this framework, one has really to implement that. And I'm a little bit scared to work on this because it's just, you know, such a treacherous topic. But here, kind of, that's the idea which I kind of displayed a lot of time, actually 10 years ago already in a YouTube video. What happens is, so this is in this case, when we take this ball, two-dimensional ball with boundaries, that's a boundary, right, a circular boundary. In this case, the Fisk manifold is just a point because this is a degree 5 vertex. So we want to get rid of this. What we can do is we can do edge refinement. We are not allowed to do the refinement of the boundary, right, because we want to color the boundary. We don't want to change the boundary because that's the goal, to keep that boundary the same. So what we can do is we can take 1 and then 2. After 2 edge refinements already, what you have achieved is that every vertex degree is now even. So there's no Fisk manifold anymore. So now we can color using this Hewood idea. You color one triangle, you flip around, go around and color everything. And then you have also colored the boundary. And that's, I showed that in the, animated that in the 3-dimensional case. Also it works, kind of, you take the Fisk manifold and then you just get rid of this Fisk manifold by just doing edge refinement. It's still kind of a, you have to constructively prove that this is really working always, and I'm convinced it works. But what might help here is just this refinement idea. Anyway, that's what I wanted to say today.